this virtual one has to look like that. It has to be symmetric across this boundary. So you have to get the boundary conditions correct for this to sound correct. So what does that mean digitally? Because you're not actually modeling this one. You're modeling this one, and you're modeling this one, which is on the boundary, but you're not modeling this one. So what do you have to do here to get this right? You have to let this be, this isn't quite a free boundary because it's...
Just connect the same line to both sides.
So does that mean you have to make this flat? Is that what that means? It means the slope... That's not quite right either though, right? Because you can have stuff, you could have a maximum at the center like you would here. And so you have to allow a slope near at the boundary. What is the right condition? I think the right condition is that it has to be loaded as if it were a piece of the membrane. So it is neither completely loose nor completely fixed. If it was completely fixed, you'd have a drum 1/4 the size. If it was completely loose, it would be like there's no drum over there at all.
If you take that and make like another node with the same connections on the left and the right, would that work?
Ah, so are you saying we really have to look at the second derivative here? Ah, so we have to look, yes, because what we really care about is a maximum here. And so what we really have to do is to look at the curvature of the last two points, and so I'm still missing something about what the boundary condition has to be, though. I can't quite get it. I'm going to have to think about this some more. Because I can't quite, I mean, if this were a completely free boundary, then there can't be any gradient along the edge, right? It's just flapping free. And if it's fixed, it's fixed. But this is not quite either one of those, and so there has to be some constraint between these two slopes. I can't quite get what it is. It's not totally free because this, or is it? Or if this edge of the drum is doing exactly the same thing, then why is it loaded at all? Oh, interesting. I have to think some more about that. I'll probably have to get back to you with an answer on that one next time, because I'm not sure what the answer is. Or is what you do is you model 1/4 plus one node. Maybe that's what it is. You model 1/4 plus one node, and force that node to be the same as this one. Yeah, that does it, I think. Okay, that's a head scratcher. Maybe it's time to, before you actually put that in Verilog, you might want to try it in MATLAB. All right, and see what it sounds like. See if the spectral property is the same. Maybe I'll do that too, because that's an interesting question. What other questions about the do you have about this project so far? One question I had today was, is it possible to put 100 nodes completely parallel on the DE2? So, and the answer is I don't actually know. We can do various metrics. We can say that you have to store something like 60 bits per state machine minimum, because you need probably 3 18-bit words plus a few other bits to run one state machine, because you need a register for the current sample, a register for the last sample, and a register for the sample before that, since it's a second order system. So we need something like 60 bits. There are a total of excuse me, there's about 35,000, 35 times 10 to the third bits in terms of logic elements on the board, and here we need about 60. So in round numbers, that says that we can do about 500 nodes, it looks like. Right? So 10 by 10 is possible, but not too much bigger than that. Maybe, well, 20 by 20 maybe. Now, that's only for memory. It's not quite clear to me how much it's going to take for each state machine in terms of logic elements. Has anybody scaled that out yet, or built one to see how big how one state machine is going to be? The main, yeah.
Just remember when I did it, we used the fine grain approach and we got 19 by 19, so that's actually about right.
So you can do 19 by 19 by doing the most straightforward thing, which is to build a state machine that executes one node. Okay, and so the state machines were idle most of the time, because they were not updating. They were updating once every 1,000 cycles, and it took probably 40 or 50 cycles to run the state machine, something of that sort. So it is completely doable, completely in parallel as a fine-grained exercise. Did you hand wire those, or did you use a generate?
Yeah, generate is crucial.
Crucial, otherwise you go nuts wiring up 400 of the things. This assumes that you use no multiplies. This assumes that you get very clever and do everything as shifts and adds. So you have to do a multiply by row and by 1 minus eta delta t over 2 or something of the sort. And so you have to choose the rho and choose the eta delta t carefully so that you can represent each of these multiplies by a fairly small number of shifts and adds. Now, interesting question is, if you specify a constant in a Verilog program, what does Quartus do? If you just say, if you assign this to be some bit pattern, if you assign this to be some bit pattern, what does Quartus do when you ask to do rho times some variable? Does it actually use a hardware multiplier? Or does it do the reasonable thing, look at the number of bits that are non-zero and implement this as shifts and adds? Anybody tried that? That's an easy experiment to do, to find out whether you have to whether you have to do the shift and add coding yourself or whether Quartus just does it for you. And I don't know the answer. It may be that it depends. It may be that Quartus is smart enough to say, if there's only one bit high, surely we're just going to do a shift and add. If there's 2 bits, yeah, probably. But if there's 10 bits high, it's better to instantiate a multiplier. Don't know. But I'm not asking you to make a completely general program, although you could. I'm not asking that you be able to choose rho with arbitrary precision or eta with arbitrary precision. I'm just asking you to do 2 different interesting sounding drums, minimum. In the past, people have used shifts and adds, and they have also used multipliers. But if you use multipliers, you only have 35 18-bit multipliers, unless you use the DE2115 board, in which case you have 480 18-bit multipliers, or some huge number. I think it's 480. But 35 state machines running at full speed should be enough to do something like a couple of thousand nodes, computational nodes. There's a whole bunch of interesting trade-offs in this lab. What makes it interesting? Has anybody gotten a sound out yet? Anybody implemented a 4x4 drum and gotten a sound out? Do it soon. Scale it up. Start small. You don't have to build the whole thing at once. If you get one module working, you get one node working, make a one-node drum. See what it sounds like. What would it sound like? What would it sound like? Boing?
Physically, it shouldn't sound like anything.
Physically? Well,
Because there's no air. There's nothing to vibrate air.
so I'm saying you have one computational node whose edge hooked to four points, all of which are held at 0. All right. So this thing moves up and down. Should sound a lot like a sinusoidal oscillator. So it should just decay in amplitude as depending on what damping you use here. So you could test with a one-node system. Might not be a bad idea to do that. What else? Anybody going to go for more than 18 bits precision? If you go for more than 18 bits, you have to ask then, are you going to use multipliers or not? If you're going to use multipliers, then the next obvious size to go to is 27 bits, because that's 3 times 9. The basic hardware multiplier is a 9-bit unit. So if you're going to go above 18, you should probably go to 27 bits if you're using multipliers. If you're not using multipliers, then it absolutely doesn't matter what you can use 23 bits or 22 bits or anything you want. You'll get better resolution, you'll get better sound at low amplitudes. Then you'll get more accurate attenuation at low amplitudes, and it won't matter at high amplitudes.
Does Silicon have an exponential function, or we have to approximate?
You have to approximate. There is no there are no floating point functions. There are no mathematical functions of any sort. So you're saying in the MATLAB code, I use something like e to the minus alpha r squared as the driving function for the initial strike, because it has nice spectral properties. But I think what you're probably going to want to do is to table drive it rather than do this calculation on the fly. Why not just build a table with a certain number of values in it that approximate a Gaussian and drive the system with those? This does bring up an interesting point, though, and that is you press a button, and that means that you, in principle, once you press the button, you may need to load a separate value in each of 100 nodes. And so you need a mechanism to do that. If you have separate state machines for each node, well, then it's like pressing reset on the state machine. It's going to load up the registers in the state machine with some value. So if you load up U in the state machine to be some value, and you load up U minus 1 and U minus 2 as 0, then you've effectively started the drum as if you have pressed it, held it, and then released it, because it's starting from 0 velocity. No, that's not right. No, that's not right. It's starting from no, if you set all these to be the same, you set all of them to be the same, it's like it's starting from rest. If you set these to be 0, then you've effectively put a velocity impulse onto the system. You've given it an initial velocity starting from rest position. What else?
When we change the strike position of the node, so even the Gaussian distribution will change, as well as the sample that we take out as an output to the audio codec, that will also change, right?
Well, you could strike here and take the output there. There's no particular reason why the output has to change when you change the strike position. It could. And if you strike a drum in different places, you surely do get different sounds out. But if you do that, you absolutely cannot invoke symmetry. Right? You've got no symmetric system then. Typically, if you drive a drum near the edges, you get a higher pitch out of it because you're exciting higher harmonics. If you hit in the center, you're driving the whole thing as near the fundamental mode. If you hit near the edge, you're causing more waves to propagate across. So you could make it completely flexible, strike anywhere, record anywhere. You have to have some mechanism of controlling that, of course. So you could have different presets and say, you know, these switches, I'm not asking you to have any sort of high-level user interface here, but you could say if these switches, a set of switches marches the strike point across the center line from one edge to the center. The other set of switches marches the strike point from the upper edge to the center. And the third set of switches determines where you're going to record from. But it is sufficient to strike in one place and record in one place. Or you're supposed to make two different sounds, two different timbre of drums. Another possibility is to keep these the same and strike in different positions. Lots of possibilities.
Just the initial question, do you want to excite just one point, or
you actually have to excite several points around it to avoid really bad numerical effects.
do that in like a bell?
Right. I mean, a bell pattern is nice, and a Gaussian is nice because it minimizes the bandwidth, so to speak, of the strike. But it is probably sufficient. So now I'm going to try and do this in perspective. So if we have the point we're striking here, we want to ask what we should do on the next grid points over. So you probably want to, at the very minimum, have a triangular cross-section with a strike point, and at the grid points which are adjacent to that, or going in cross-section here, let's do it this way, in cross-section, at zero distance we have unity strike. At grid distance 1, or 1 over the square root of 2, you have an amplitude of half, and at 2 grid elements you have an amplitude of 0. That is the absolute minimum you have to do to get a decent sound out of it. You can approximate an exponential by saying we're going to use amplitudes 1, 1/2, 1/4, 1/8, and do that until you get tired of it. But by the time you get down to 1/16, you've got almost all of the energy. So you could just approximate an exponential drop-off like this, and sure, the curvature is not quite right up here, but who cares? And this is nice because that means that you have only a 1-bit add or a 1-bit load to each of the initial points that you're making non-zero on the drum. Another design decision is, when you strike the drum, does it reset it to the 0 position, or does it merely add to the energy which is already there? When you strike a real drum, It's a complicated thing because you could, in principle, strike exactly out of phase with the drum energy that exists and kill it completely, right? So you could make a loud drum on the first one and hit it again and make nothing. Pretty unlikely, but it's possible. Much more likely is that you're going to get some sort of addition. You strike once, you strike again, it's louder. The total energy is higher than it was after the first strike. You're getting so you strike, you're getting a decay in energy. You strike again with the same amplitude, you get a little higher energy because you're adding what's already there. So you have to make the decision, are you going to be more physically realistic and add the energy to the existing amplitude, or are you going to just simply reset the drum to some initial condition? I don't actually say in the lab, so you can do it either way. The MATLAB code adds it. If you were going to add then these weighted values near the strike point would be just added into the current value. If you're going to make this variable, if you're going to make the strike point in the shape of this variable, then you have to figure out a way of broadcasting the current value to all of the nodes at the time of strike. What else? Well, I'm happy to see people are thinking about this. And while you're coding this up, you should probably be reading for Lab 4, because Lab 4 has a sort of a large startup transient. It has a large amount of reading that needs to be done for startup. Because I'm going to ask you to design a NIOS 2 system, and it's just a big, bulky set of development tools. I've linked up a bunch of tutorials in the Lab 4 reading, probably, well, I don't know, 6 or 7 different articles. But you don't have to read them all, but you should probably read the introductions on how to use SOPC Builder. I'm going to talk about that, but there's no substitute for reading the tutorial and going through the clicks yourself. So you're going to need to start reading, and you may as well do that before Lab 4 starts. Any more questions on Lab 3? Okay, well, let's talk about NIOS CPUs a little bit. So the basic CPU is a 32-bit CPU. It's MIPS-like. Which means that it's simple in structure. The interrupt mechanism is extremely crude. There's no vectored interrupts. It has an interrupt system, but it's not vectored. generally a simple system. You're going to design it using SOPC Builder, System on Programmable Chip. You need to read the tutorial like soon. This is going to generate your CPU Verilog, which you're then going to combine with your top-level module. So the top-level module is going to allow the CPU to talk to the real world. So the CPU might then have an interface for the LCD display that's on the board, but it can't get to the LCD display unless the top level enables the LCD display. So you're going to feed in a CPU description in the top level into Quartus 2, of course. And then out of that's going to come an SOF file, which you're going to download to the FPGA, and that's going to have the description of the CPU, but then you, of course, also have to write the C code. And there are now two different ways of doing that. One is the NIOS 2 IDE, Integrated Development Environment. This thing's a monster, but you can do whatever you want with it. Then there's a separate thing called the Altera Monitor, which I haven't played with very much. I played with the beta version a couple of years ago, and it didn't do enough, so I went back to the IDE. But I suspect this is more mature now. I'm going to start playing with it. I'll be able to tell you in a week or two. But you may have already figured it out for yourself then. So there are two different ways now of generating C code. So the input to this is C code. Or if you're feeling really brave, you can code in assembler, in MIPS assembler. And then this is either going to be downloaded to the FPGA or to SDRAM, depending on exactly how you want to execute this. However, if you download to SDRAM, you need to read the SDRAM tutorial, which is also linked up in Lab 4. So you need to read the SDRAM tutorial. There's a usage document on IDE. There's a tutorial for the Altera Monitor. There is a tutorial for SOPC Builder. You need to read all of it. SOPC Builder allows you to specify peripherals. So obviously you're going to have a CPU. Every SOPC design has a CPU, but you can also specify a JTAG UART. This is a very special and somewhat weird I/O device for the CPU, because it allows you to communicate serial information from a printf, for instance, from a high-level construct like a printf, through a secret channel inside the CPU, through the JTAG cable that you use to program the FPGA. So there's this weirdness that the same cable you use to program the FPGA becomes the serial communication to the high-level CPU. And when you do that, you can type into a console window, a special console window, and use the JTAG UART as an I/O device. There's also a regular UART, which goes through the serial connector on the board. There's a serial peripheral interface device, an SDRAM driver, which obviously you're going to use for SD-RAM. There's a flash driver, which I doubt if you'll use in this course. An LCD driver, which you will use. So how many people are familiar with Unix stream devices? Stream I/O. So you've done some other people? You know, in Unix everything's a file, right? Every I/O device just looks like a file. Anything you can do with a file, you can do with an I/O device, vice versa. And as far as the NIOS2 code goes, the C code goes, the LCD just looks like a Unix stream device, and so printf and everything else just work. So you can do printfs to the LCD and no special cleverness necessary, except you have to open the device as if it were a file. There's parallel I/O channels. These can be 16 or 32-bit. I think they can even be 8-bit. So you can build as many of these as you want. So you can have as many I/O channels as you want off of this chip. Unlike commodity microcontrollers that limit you to 2 or 4 or 8 channels, you can have 100 I/O channels if you want. There's a timer. I wouldn't say they're very good timers. They're interval timers only. You can't use them very well for capture events or for high-speed synthesis, but you can certainly use them to run an operating system, interrupt, and to generally keep track of time. The timer interrupts on this microcontroller take about between 200 and 400 cycles to take the interrupt. So after the timer ticks and throws an interrupt, it's 200 to 400 cycles before your interrupt service routine starts to execute. It's a long time. So in SOPC Builder, you generate a memory map for all the peripherals you want to include. And it's a visual thing, so you get to see the structure of the memory map in a fairly graphical kind of way. So you generate a memory map for the I/O, and all of that input-output is in fact mapped as if it were memory devices. Question back there? About SOPC Builder? Are you enthused or vaguely queasy? Vaguely queasy, yes. A reasonable thing. You get to name each peripheral. And the reason I'm putting this in uppercase is that whether you use lowercase, uppercase, or mixed case in SOPC Builder, the output of SOPC Builder always uppercases it. It's ugly. So you may as well give the names in uppercase. These names are passed off to the C compiler, and you can then use them in the IDE. You can use the names you've assigned in the IDE as device names. In the Altera monitor, it's not clear that you can do that. You may have to use absolute I/O addresses. If the device has an interrupt associated with it, then you can specify an interrupt number for the device, for each device that you put in. Not all devices support interrupts, but many do. Timer does, UART does, SPI does. You can optionally associate an interrupt vector or an interrupt number, it's not actually a vector, you have to specify a reset address, which is usually 0. And an exception address, the only time it's not 0 here is if you're defining multiple CPUs, which you can do, then each CPU has to have a unique reset vector, and the value of the reset vector specifies the boundary of the memory associated with each CPU. You have to specify an exception vector address, and this is usually set to 0 hex 20. And every exception, hardware, software, and otherwise, goes through that same location. So the output of SOPC Builder is a descriptor file, which is passed off to the compiler, and a very large amount of Verilog, which generates all of the interfaces that you specified, but you can't read it because it's encrypted. And so Quartus 2 can read it. Quartus 2 can read it, but you can't. So you can't say, oh, I wonder how you write it. It would be very nice if you could see how to write a 32-bit CPU and how the very sophisticated bus structure works. This so-called the Altera, what is it? I've just lost the name of the bus. It's lovely getting old. Anyway, the very nice bus structure. You can't look at any of that. If you want to, optionally in SOPC Builder, you can add instructions to the CPU. If you want to, you can add hardware to the CPU. You can write your own bus-oriented I/O using a module generator for SOPC Builder. And some people have done that for final projects. Yeah? Avalon, there we go, thank you, Avalon bus. Yeah, mumble mumble. It's pretty cool. It's complicated though. You've got to practice. That's why I'm giving you a whole extra week. This is a 3-week lab. That extra week is so you can practice building NIOS systems. Start soon. The NIOS IDE is installed. The Altera monitor depends upon having Quartus 2 and the NIOS IDE both installed. All of these things are completely dependent on version. So version 10.1 of Quartus 2 will absolutely not work with 11.0 of the IDE, for instance. If you have 11.0, if you download onto your laptop Quartus 11.0, you must also get the 11.0 IDE and the 11.0 Altera monitor, and you have to load them in that order. You have to download this first, then this, then this. I would say that for Lab 4, your goal for the first week of the lab, when you come into lab at the end of the first week, you should have a running CPU running a program that blinks lights on the board. That's all it's got to do. Or it puts a hello world on the LCD. That's all it's got to do. Or it puts a hello world on the LCD and a debug message on the console. That would be a reasonable goal for the first week. It's going to take you the whole first week to do it. Have I emphasized that enough? Have I scared you? Okay. Start reading. Any questions about again about Lab 3 now? Yeah.
Does that start when the beginning of fall break?
Pardon me?
Does that start when fall break ends? Like first week?
Well, since our lab is on Friday, it does not overlap fall break, and so there's no break in the schedule. Right. So, yes, I'm not asking you to work over fall break. That would be wrong. But you better come back dancing on Tuesday. All right.